Hello friends, Mr. Burrell here. We're in Unit 6. In Unit 6.1, we talked about looking at rational graphs and looking at the graphs and determining some of the characteristics of those graphs. Here in Section 2, 6.2, we're going to talk about identifying those same characteristics like the domain, the x-intercepts, the holes, and the vertical asymptotes. Except without the graphs, we're going to identify those just using the equations. We'll talk about how we find these different characteristics from rational equations. So, by the end of this lesson, these are the things that I want you to be able to know. I want you to be able to identify the domain of a function using the function's equation, identify the holes of a function using the function's equation, identify the vertical asymptotes of a function using the function's equation, and identify the x-intercepts of a function using a function's equation. Those are the things I want us to be able to do at the end of this lesson. These are kind of the same characteristics we identified in 6.1, but now we're identifying them from the equations. Okay, so let's give ourselves a little bit of a reminder. Let me move my face here. When I talk about the domain is all the possible x values for a given function. Or in other words, any number that will give an answer for x. So to find the domain in the case of rational equations, the domain is everything. The domain includes all real numbers except any number that would make the fraction divide by 0, anywhere there is a vertical asymptote or a hole. In Unit 5, we called these values excluded values. So basically, any place that would make me divide by 0, we don't like that. That doesn't work. Those are exceptions to the domain of my function. So, in order to find the domain of the function, I set the denominator equal to 0 and solve for the variable. So, the instructions on these questions say, state the domain of the following rational functions. I'm going to just be doing this first equation. If you want to do this second equation, you can kind of experiment with that one for practice. But in order to set the denominator equal to 0, and later we're going to be setting the numerator or the top equal to 0, let's go ahead and factor both of these expressions. So in the bottom, if I take out a greatest common factor out of the bottom here, I'm left with 4x times x plus 1. In the top, if I take out a greatest common factor, I'm left with x squared minus 3x plus 2. And then if I want to factor this even further, this is a quadratic expression, so I'll multiply my first and my last numbers, which is 2. Find two numbers that multiply to make 2 and add up to negative 3 right here. So two numbers that multiply to make 2 and add up to negative 3 are negative 2 and negative 1. Negative 2 times negative 1 is positive 2. Negative 2 plus negative 1 is negative 3. So my factors here, I have this x on the outside, and then I have x minus 2 over 1, and x minus 1 over 1. But dividing by 1, dividing by a in both those cases is kind of redundant. So I have x times x minus 2 times x minus 1 over 4x times x plus 1. This equation we're going to use throughout the rest of explaining all of these characteristics. So if you have the guided notes in front of you, these are the problems that we will be doing. So, to find the domain, or specifically the numbers that aren't in the domain, I'm going to set the denominator equal to 0. So I have two factors in the denominator. I'm going to set 4x equal to 0, and I'm going to set x plus 1 equal to 0. So when I solve for x in each of these cases, divide by 4, subtract 1, I get x is equal to 0 and negative 1. So in Unit 5, I would have called these my excluded values. My excluded values, now I'm going to relate them specifically to the exceptions to our domain. So if I were asked as a test question what the domain of this rational function is, I would say x, there's two ways I could write this. Either x does not equal 0 and x does not equal negative 1. That would be one way I could write the domain. I could also write the domain. This is how we wrote the domain in other classes, and this is often how it's viewed on the ACT. I could write negative infinity up to negative 1, from negative 1 to 0, and from 0 to infinity. So my domain is everything from negative infinity to positive infinity except for negative 1 and 0. Negative 1 and 0 are the only values that aren't in the domain because they make me divide by 0. They are my excluded values. That's how I determine the domain of a rational function. Okay, Next, my x-intercepts. My x-intercept is any x value which would cause the graph to intercept the x-axis. That's what an x-intercept is. It's any place where the graph crosses or intercepts the x-axis. So to find the x-intercept, this is what I'm going to do. I'm going to set the numerator equal to 0 and solve for x. So to find the holes in my domain, the exceptions to my domain, I set the denominator equal to 0. For my x-intercepts, I'm going to set the numerator equal to 0. And then I'm going to cross out any values which were already excluded from the domain, because if I have a value that's not in the domain, I can't have it as an x-intercept. So, same problem I had before. Number 3 here is the same problem I had before. I'm going to find the x-intercepts. So if I write this in factored form again, I have x times x minus 2 times x minus 1 in the top, and 4x times x plus 1 in the bottom. I determined that my domain, my excluded values, was that x is not equal to 0 and x is not equal to negative 1. So that we already determined that. So to find my x-intercepts, I'm going to set, my x-intercepts, I'm going to set the numerator, or the tops of this fraction equal to 0. I have 1, 2, 3 factors in the top of this fraction. So I'm going to go ahead and set each of them equal to 0. X equals 0, x minus 2 equals 0, x minus 1 equals 0. So my x-intercepts are going to be at x equals 0, 1, and 2. Because if I add 2 on both sides, add 1 on both sides, I get x-intercepts of 0, 1, and 2. So those would be my x-intercepts. The last part of the instructions here is I need to cross out any values that are already excluded from the domain. So any values that were not in my domain, or any excluded values, cannot also be x-intercepts. We talked about this in Unit 5. If I have a solution or an x-intercept that is also an excluded value, or not in the domain, it doesn't work. So x equals 0 here, since it was also a number not in the domain, that is not going to work as an x-intercept, so my only x-intercepts are 1 and 2. So for x-intercepts, I set the numerator equal to 0, and then basically cross out any excluded values, or any values excluded from the domain. That's how I find the x-intercept of a rational function given the equation. Okay, next we're going to talk about holes. So remember from 6.1, a hole in a graph was a point on the graph where the function isn't defined. On the graph that looks like an actual hole drawn in the function's graph. It looks like something like this. A hole is a point on the graph where the function isn't defined. So, to find a hole, any factors that cancel out from the numerator and the denominator, so any factors that cancel out in the top and in the bottom, create a hole instead of a vertical asymptote. So any numerators or any factors that canceled out in the numerator and in the denominator create a hole in my graph. So I set those factors equal to 0 and I solve. Okay, let's find the holes of this rational function. Again, we have the exact same function. Let me write out the factors again. X times x minus 2 times x minus 1 over 4x times x plus 1. Okay. So, to find the holes in this graph, the holes in this function, I'm trying to find where the function isn't defined. So I'm going to look at any factors that would cancel out. Any factors that would cancel out in the top and in the bottom, the numerator and the denominator. So notice here, I can cancel out an x. These x's right here I can cancel out in the top and in the bottom. So those factors that cancel out, I'm going to set that factor equal to 0. And that point, x equals 0, is going to represent my hole. The hole in my graph is at x equals 0. That point at x equals 0 is not defined. And if you go back here, remember, in my domain, x equals 0 was a point that's not defined. So that specific point turns out to be a hole in this graph. So on the picture, it would look like a little hole at x equals 0. That's how you find the hole in a rational graph based on its equation. Okay, lastly, we're going to talk about finding a vertical asymptote. A vertical asymptote is an x value where the function isn't defined. So just like a hole, vertical asymptote is where the graph isn't defined. So this presents itself as a vertical line that the graph approaches but never touches. So in 6.1 we talked about these dotted lines, that if a graph got really close to this line but never touched it, that would be a vertical asymptote. So to find a vertical asymptote, I set the rest of the denominator equal to 0 and I solve. So, again, back to this original equation. When I write this equation, this is the same one, when I write it in factored form, I have x times x minus 2 times x minus 1 over 4x times x plus 1. So, just as a refresher, my domain was all the real numbers except for 0 and negative 1. My domain was everything but 0 and negative 1. What did I talk about next? My x-intercepts were 2, x equals 1 and 2. When I set the numerator equal to 0, I got x-intercepts of 1 and 2. My hole in this graph is at x equals 0. That was one of the places that didn't satisfy my domain, and it ended up being a hole because it canceled out in the top and in the bottom. That factor canceled out and in the top and in the bottom. So now, to find my vertical asymptotes, I set the rest of the denominator, the rest of the factors that are left in the denominator, equal to 0. So after I cancel things out, the only factor I have left is x plus 1. So when I set x plus 1 equal to 0 and solve, subtract 1 on both sides, I get a vertical asymptote at x equals negative 1. I get a vertical asymptote at x equals negative 1. Right here. All right, I wanted to quickly pull up on Desmos what this graph looks like. Later in this unit, we're going to talk about graphing these rational functions, but I just pulled up this graph, and I want you to notice some things. So, my domain of my graph was x is not 0 or negative 1. So notice at negative 1, at x equals negative 1, I can kind of see that as I go up and down at negative 1, the graph never actually touches x equals negative 1. It gets so close, but it never actually touches. I have x-intercepts at x equals 1 and 2. Those are my x-intercepts that I found, 1 and 2. I have a hole at x equals 0. Check this out. Right there. At x equals 0, my graph is undefined, so I have a little hole. See that little hole that Desmos gives me? And then my vertical asymptote, that vertical line that the graph gets really close to but never touches, is at x equals negative 1. Right here. At negative 1, my graph, negative 1 right here, my graph gets really close to but never touches. So we found all of those characteristics of this graph without even looking at the graph, just from looking at the equation. That's pretty cool. That is pretty cool. Okay. So, I'm going to skip over that question for now. So, in the next page of your guided notes, at the bottom, it says rational equations, and then I want us to find the domain, the holes, the vertical asymptotes, and the x-intercepts for these rational functions. So, let's find, we'll go in this specific order. We'll find the holes, the vertical asymptotes, the domain, and then the x-intercepts. So this function is already factored. Everything is already factored, so I can get started. So, remember, my holes. In order to find a hole is a point on the graph that isn't defined. So it's a point on the graph that would make me divide by 0 in my function. And specifically, I find a hole by identifying any factors that cancel out. So I can cancel out an x plus 4 in the top and in the bottom. So solving x plus 4 equals 0 will give me where the hole in my graph is. So my hole is at x equals negative 4. My hole is at x equals negative 4. My vertical asymptote is also another place where my graph isn't defined. So looking at the factor that's left in the denominator, I'm going to set x plus 1 equal to 0, and I get a vertical asymptote of x equals negative 1. I get a hole at x equals negative 4 and a vertical asymptote at x equals negative 1. Here's a hole, here's a vertical asymptote. My domain is all real numbers, all my x values, except for negative 4 and negative 1. Those are the two values that would give me either a hole or a vertical asymptote. Those are the two values that would make me divide by 0, so those values are not in my domain. Or you could write this as negative infinity up to negative 4, from negative 4 to negative 1, and from negative 1 to positive infinity. Either way of writing the domain in that case is fine by me. So the domain is found by setting the denominators equal to 0. Then my x-intercepts, I set the numerator equal to 0, and then cross out any values that are not in the domain. So this x plus 4, this ends up not being in the domain because it cancels out here. So I find my x-intercept by setting the remaining factor in the top, x plus 2, equal to 0, which gives me an x-intercept of x equals negative 2. So my graph would cross the x-axis at x equals negative 2. So this number right here gave me my hole. This factor right here gave me my vertical asymptote. These factors right here gave me the numbers not in the domain. And then this remaining factor in the top gave me my x-intercept. Mr. Burrell, what do we do with this negative 3? Basically, that negative 3 is trash. It's not going to affect the hole, the vertical asymptote, the domain, or the x-intercept. It might change a little bit about how the function looks, but these characteristics will not change. So you don't have to worry about it. Throw it away. Ignore it. It's not going to affect any of these different characteristics. So looking at this graph, let me erase this domain right here. This is the actual graph of this function. This was in your guided notes. Look, I have a hole at x equals negative 4. I have a vertical asymptote at x equals negative 1. My domain is all numbers except for negative 4 and negative 1. And I have an x-intercept at x equals negative 2. So I found all those characteristics just looking at the equations. That's pretty cool. So hopefully by the end of this video, by the end of this lesson, these are the things that you understand. I want you to be able to identify the domain of a function using the equation, the holes of a function, the vertical asymptotes of a function, and the x-intercepts of a function, all from the equation. So I hope that was helpful. Please reach out to me if you have any questions whatsoever, and I hope that you enjoyed that as much as I did.